Here we go. So today we'll be talking about wave optics. The last thing that we did was we talked about geometric optics, which is basically like you have rays, light rays that are going in particular directions. We did go into some of the quantum mechanics of that, where you actually have the phase advancing, the phase of the wave function, or in this case, the phase of the photons, literally the phase of the wave as it's propagating. And then what you see, where you see the image, is the sum of all of the possible trajectories of that light, but only those that add coherently, where they add in phase with each other, do you actually get the image. And so that led into the formation of diffraction gratings, where I seem to recall doing a picture that looks something along the lines of here you have some source, here you have some object, and then you have these different mirror surfaces. These are all equally spaced. Pretend that these are equally spaced, even though they're not. And then what you'll get, say you have a particular color, these things will combine at this distance where all of these paths are integer multiples of each other. And so you can do this because because they're equally spaced. So all of these paths are going to be integer multiples of a particular wavelength for a particular color of light. If you talk about a different color of light, then it will actually, they will add coherently or in phase with each other at a different distance. And so you can have something set up like this, where you'll get, say, blue light here and red light here. So a diffraction grating takes the light and splits it into its different component parts, because the light bouncing off of each of these surfaces, it's only those wavelengths that add constructively at a given distance where you'll form the image. So you can take white light, break it into its constituent colors in a spectrograph, which involves having a diffraction grating like this. Let's see. So there was another. So we covered that, which is mixing together ray optics, geometric optics, and wave optics, which is what we're going to be talking about today. So wave optics. Let me pull up the book. Look at the size of that pointer. It's amazing. What do we need to talk about? Talk about the wave aspect. Like, how do we know that light is a wave when it's actually not a wave? But how do we know that it follows the wave equation? And the answer is because it obeys certain wave-like properties. I can't get the edge here to grab. So that's unfortunate. I can get that edge to grab, but not this one. Let me move it a little bit. All right, well, I guess I'll just slide the whole thing over. It's too big. The mouse is way too big to grab the edge. All right, so here we go. But we have wave optics. So we'll talk about how we know that light is a wave, and then we will look at this Huygens principle, which is important. The Huygens principle, we did the Young double slit experiment, so that's what we'll talk about. So I guess we'll start with the Huygens principle, then we'll do the Young's double slit experiment, and then we'll talk about diffraction and thin film interference. Polarization we don't need to worry about because we've already talked about polarization, and that will leave us, so we'll wrap this thing up here, and that will leave us ready to go on Thursday with special relativity. Special relativity on Thursday. Excuse me. Let's get started then with wave optics. So Huygens principle stateth the following thing. Huygens principle says that if you have a front, so here is a light ray that's moving, a wave front, or a light ray that's moving like this. What you can do is you can treat every individual point on that wavefront as its own individual point source. So everything here is a point source that's radiating actually in all different directions. So each of these points is radiating light in all possible directions simultaneously. And the reason that you can do this, or what happens when you do this, is that those components that are coming off at weird angles, if you have a complete, like a full wavefront like this, those things that are coming off at weird angles will add destructively. They will destructively interfere with each other fairly quickly. Like this one here going off at that angle will interfere with the light here that's coming off at not a parallel angle, but a slightly similar angle, so they'll interfere at different distances. And so they eventually cancel. The effects of the waves, so these are all waves that are propagating, and the effects of nearby points that are moving where the wave is coming off in a different direction than straight forward, they're going to interfere with each other and cancel each other out. And when you have a full wavefront, all of those things are going to combine to give you to propagate the planar wavefront, because these are the only parts that, it's only those that are moving in the forward direction, only those wavefronts that are emanating from each individual point source here, only those that are pointed straight forward are going to add coherently. And so that propagates a planar wavefront forward and maintains its integrity, maintains its structure as a plane. However, when you have edges, so you have a plane wavefront like this, the ones in the middle here, the points in the middle, they will continue to propagate the wavefront straightforwardly, but then you're going to start getting edge effects. So the point over here, it's going to be emitting light in a whole bunch of directions like this, but it doesn't have any neighbors on this side, neighbor point sources on this side that can cancel some of the effects. And so you get edge effects. It comes along here, and then you start to get the behavior of the wavefront changes as you go towards the edge. This is diffraction. So when you have a reflected beam, the edge effects create, things don't combine the same way that they do when they're in the middle, and you have portions of the wavefront that are uniform in intensity. Here you have an abrupt transition at the edge of the wavefront. You have an abrupt transition from emitting surface to non-emitting surface, and that creates these edge effects that actually move inwards and blur your image. So when you have a telescope, for example, here is your telescope like this. This is the mirror of your telescope. You have light coming in from all directions like that, and then it hits the telescope and gets reflected inwards like this, but all of the points in the middle of the telescope, all these ones, have neighboring points, and so they're going to add constructively, it's going to respond as though you have a single wavefront that is propagating towards the center. However, at the edges over here, these points don't have neighbors on this side, and so they add differently, and you get the destructive, or you get the interference effects along the edge that blurs the image that you have at the focus. So along the center, you have a well-behaved wavefront that bounces off the mirror and propagates towards your detector. At the edges, you have poorly behaved wavefronts because there's an abrupt change in the nature of the sources of light. Here, the light just passes by, doesn't reflect, and so the photons that are bouncing off of this edge of the mirror don't have neighboring sources that will combine to produce a good high-quality image. And so that creates edge effects that are called diffraction. So it limits what you can observe because you get blurring from the edges. So that's a diffraction effects are edge effects. Fundamentally, they are from interference, and that's what we'll talk about next. After I don't have any beverage. Okay, I guess I'm going to be thirsty for this stream, but that's fine. So let's talk about what interference actually is, and then we'll come back to this. So interference, you have two waves like this wave and this wave. They can add together in a variety of waves. It's okay. I only have, I can pull through. I can pull through. These waves can add coherently. So in this case, they're adding in phase. So you have this part and this part combining, and this part and this part combining, and so you're going to get a combined wave that has more amplitude than otherwise. You can have a wave where one of the waves is like this, and the other wave is exactly the opposite, like that. So now where this one is high, this one is low, and then when these two things combine together, you get no effect. There's no wiggling taking place here. So you can, as you have different waves, even different waves of different wavelengths, they can combine. The fact of the matter is that they add these amplitudes, the wave amplitudes combine, that you just add them together. And the phases combine in such a way that you get interference properties. So interference doesn't mean that it causes destruction of everything. There's constructive interference and destructive interference and everything in between. So constructive interference looks like this, where you add them together and they combine. Because they're in phase, you get a larger amplitude, which means you have more intense light. And then you have destructive interference when the two waves are coming out of phase and they essentially destroy each other. You get no effect in that case. And this is a wave, a property of waves is that they obey these interference principles. And so sound waves with noise canceling headphones, you have your headphone, here's your headphone, it has a little microphone out here, here's your head, it's nice and shiny, here's your shiny head, as you're listening to your noise canceling headphones and you're smiling because of the noise cancellation. So it has a little microphone on it. You have all this noise coming out here, or as the French would say, la bruit out here, coming in and trying to disturb you while you're on the airplane. And so this microphone picks up these wavefronts and then drives the speaker here out of phase with those wavefronts and cancels out the noise. And then, so it senses what the wavefront is coming in, it drives the speaker out of phase with it and cancels out the noise, so you get very little noise coming through. And the same thing happens on the other ear, where again you have a microphone and it cancels out the noise coming in here, and it makes everything really quiet, if you dig that kind of thing. So that is how noise canceling headphones work, and it's exactly the same thing. It's using the fact that waves interfere with each other. You can add waves together so that they combine properly. You can add waves together so that they combine in phase and therefore amplify one another, or I should say sum together, or they can add out of phase and essentially destroy each other. It's noise canceling headphones is, well, you never know if it's forwarded to the NSA servers so that they can hear all of the noise, background noise on the airplane flight. And you can have everything in between. So you could have one wave like this and another wave that is either slightly out of phase. Oh, that's not slightly out of phase. I wanted it to actually be out of phase slightly. So like this. And the sum of this is going to be, maybe some small amplitude wave when you add these two things together. You could imagine having them at different wavelengths. So here's one wave like this, and you have another wave that's a slightly different wavelength, where it will add destructively here. So destructively here, where you have this one going down and this one going up, and then definitely destructively here, where that one's going down, that one's going up. But then you have them add constructively over here, and so you can get patterns that are like this, like beat frequencies. So these beat frequencies appear also from an interference pattern. These are all interference patterns, or all effects of interference. So with interference, that's something that waves do, and this is how the wave-like property of light was discovered. Is that Mr. Young set up the double slit experiment. So you begin with Huygens principle, where you have light coming in. So here's light coming in like this. It's moving in this particular direction. These are the wave crests of the light as they come in, and then you restrict it so that the light can only go through two individual ports, or two individual holes, or slits. It was slits because it was the double slit experiment. If it was holes, it would have been called the Young double holes experiment. One of the reasons you want to do slits is that, well, I'll show you why you want to use slits in a moment. So the Young's double slit experiment, a light comes in, hits these things, and then you basically say, okay, this acts like a point source, and this aperture acts like a point source, and so now you have light that's radiating in all directions, like this. And as a consequence, you're going to have locations in the distance. So here's your detector screen. You're going to have locations where this wave, or that wavefront, and this wavefront combine together to give a bright source. And then you're going to have places where, so they add constructively there, and you're going to have places nearby where they add destructively. And so you're going to get a pattern of intensity pattern on this surface where it's like, well, where am I going to draw it? I guess here, like bright, dim, bright, dim. So you get something that looks like this. Bright, dim, bright, dim, bright, dim. Okay, so you get this repeating intensity pattern, and that is from the wave-like properties. And that demonstrated that light was a wave, even though light's actually a particle. But it's a particle where the probability density obeys the wave equation, or the probability amplitude obeys the wave equation, and then you square it and get that. Let's see. That's basically interference. Now, the reason that they chose to do, or he chose to use a double slit instead of a double hole, is if you have a hole like this, the light coming out from this hole has that diffraction problem at every point, right? So you have a hole that's coming out, you have a spherical or circularly expanding wavefront here and a circularly expanding wavefront here, and that's going to produce a weird intensity pattern at a distance. So if we look at interfering ripples in a pond, interfering ripple is in pond. Okay, you can see here, for example, how the pattern is more challenging to analyze, more challenging to look at. Where if you have a slit instead, so here is a slit and here's another slit, then you're only going to get the interference pattern in one of the directions. It's constricted in this direction, So your light is constricted in this direction, which gives you two basically point sources, but it's not constricted in this direction, which doesn't create the interference effect. And so then you're going to get an intensity pattern that has bands in it that are easier to analyze. Okay, so it turns out that what happens when you have any aperture, let's see, do I want to talk about this now? I guess I'll talk about this now. When you have any aperture, you're going to get edge effects for the reasons that I described. Every point in this aperture is going to act like a single point source. All of these ones have neighbors and therefore are going to behave or act like a source of rays. But the ones on the edges don't have neighbors, and so they're going to act like diffraction spots. They're going to act like locations where the wave is going to propagate out in all directions, but it doesn't have the neighboring counterparts that are going to cause it to behave like a wavefront, and instead it's going to behave like a spherically emitting source. Okay, and so it's these edge effects that create diffraction patterns. The smaller, what's going to happen is the smaller the aperture that you squeeze the light through, right? So you have a beam of light coming straight through this square area. We'll call it a rectangular area because that's going to be useful in a moment. So you have 1,000 points of light that are all emitting stuff coming out of here. It will act like a beam coming from the center regions, and the edges is going to create your diffraction problems. And that diffraction comes from interference. It comes from the lack of interference of sources of light outside of your aperture. Okay, with this, what's going to happen? The more you restrict the aperture, so the smaller you make the aperture hole, the more spread out it's going to get. So the spot that you get is going to spread out. So if you have a small aperture hole like this, you might create a spot that is like that in size. So the light is going to spread out because you've got more spherically emitting sources than you have ones that are going to emit like a plane. So you make it smaller, you make it even smaller, and it's going to spread out. The light's going to spread out even more. So to the point where once you get to a point source, then it's going to the light's going to spread out like a hemisphere. So if you have a single point source, the light is going to spread out in all directions like a hemisphere. Another way, I guess, maybe a better way to draw this would be, here's a point source, and the light is going to spread out like this, okay, in all directions. If you open it up a little bit, let's do it with a circle. If you open it up a little bit, then it's going to spread out less. So this one is going to spread out in all directions. This one's going to spread out in kind of a cone. And if the hole is big enough, then it's basically going to act like a collimated beam like this. And it's only when you constrict the size of the hole. But the question is, what does it mean for the size of the hole? Like, what's a big hole and what's a small hole? Is it big compared to the Earth? Is it big compared to the sun? The sun's pretty big. If you have a hole that's bigger than the sun, how's that going to behave? Or, what's the length scale that determines what it means to have a large hole versus a small hole? And the answer is the only other length scale that you have available to you is the wavelength of the light. So that the wavelength of the light is denoted by the Greek letter chicken-foot. And chicken-foot tells you how long is the wavelength. And the question is, how big is this aperture compared to the wavelength of light that's passing through it? So an aperture that is this big, and like physically that big, so that's about yay big. An aperture that is this big is going to create what's it going to do? An aperture that's that big, if you have a wavelength of light that is like 0.5 micron, so half a micron, is going to be small. And so this is a gigantic aperture, and you're going to get a behavior that looks like this right here. So you get this big collimated beam. On the other hand, if this is the size of your hole, but you're putting kilometer-sized wavelengths through it, then this is tiny. And so the real important thing is, what is the diameter of the hole? The diameter of the hole, or the width or the length of the hole if you have a square hole. It's the diameter of the hole divided by chicken-foot, the wavelength of light. Okay, this is the criterion that you use to determine, what's going to happen. When can you not see stuff anymore? When does the blurriness come in? So you go from having a collimated beam like this to having a beam that disperses like that. Okay, so here are some questions. Just remove the edges. That is one way to do that. It's wild you can cover the other slit, get the light in places in the backplate where there wasn't any, both slits were open. Okay, so I will talk about that in a moment. If you take the slit, mark off the diffraction pattern on the target, what happens if you add the slit where the diffraction pattern hit and the other? Okay, so what happens, let me see if I can answer properly what these questions, or at least something related to these questions to make it sound like I answered the questions even if I wasn't able to answer them properly. And then you can tell me if this actually answers your question. One thing that was found is, and you can do the same thing with electrons, right? Electrons are quantum properties. They behave, they follow the Schrodinger equation, which is a wave equation. And so electrons also have wave-like properties. And so you can set up a double slit experiment. Here's a double slit experiment. And now you're using electrons. So you have an electron gun. That's called a cathode ray tube. I know that this has changed definitions lately. The CRT has changed definitions lately, but in this case, this is a cathode ray tube. So you have this beam of electrons that are coming out here. You can send the electrons one at a time, and the electrons obey the Schrodinger equation, which is how does the probability distribution of these things, or the probability amplitude, propagate in space, and it satisfies this complex wave equation. And so you're going to have these electrons will go through these two slits, and you'll actually build up a similar diffraction pattern, right? This is the intensity as a function of position relative to, so you have a screen here and you're going to get bright bands and dark bands. So you can actually send electrons one at a time. You can send electrons one at a time through these slits, and they'll just sit there and populate regions of, on your detector, and not populate other ones. It's quite strange to look at. So let me see if I can pull up an example of that. So let's go with electron double slit experiment. They've done it with whole molecules. I don't know if they've done the double slit experiment with whole molecules. I suppose, maybe they have. It doesn't sound like a trivial thing to do because the molecules have very short coherence lengths. So getting them to add constructively is harder to do than it is with electrons. Let's see, where are the images? So these are the this is what I showed before. So in this one, the interference pattern is this part in the middle. That is the interference pattern. The diffraction pattern, which I haven't gone into detail about other than that I just said that it exists. The diffraction pattern is this overall envelope. The fact that you have a bright thing in the middle and then a bump here and another bump there. The interference pattern is these smaller tick marks, like the smaller hatchings of this thing. So let's see if it has the electron. So this is individual particle detections. I wish I could pause this, but I can't. So, but you can see at the beginning, it looks like it's all, it looks like it's random at the very beginning of this animation, and then it starts to fill in only certain parts and leave other parts empty. And so this means that a single electron, because this is just individual single electrons that are going through this apparatus and getting to the detector. This is probably a simulation. I don't know if it's a real experiment, but it's what they see in simulation. I'm sure that there's a image in here somewhere. Maybe. No, okay. I guess I can pull up the image that I'm looking for, which is this one. So here you can see, here is the beginning. Can I open up this one? Open in new tab, like yay. Okay, so it starts here. You see only a few dots, and then over time you see more dots, and it seems like it's covering most of the space. But then as you keep building up, you find that you get regions of overdense regions and underdense regions. So this is building up from firing single electrons. What does that imply? What that implies, if you're firing single electrons and building up this interference pattern, that implies that the individual electrons travel through both slits. The electrons travel through both slits as they move forward. Specifically, the wave function for the electron. So here's the wave function for the electron, the spatial wave function. It's propagating in this direction, but it's got some spatial extent to it because that's, it actually extends to infinity. It has non-zero probability going up to infinity. So the wave function that describes the probability of measuring the wave or the electron at a given point extends all the way to plus and minus infinity in all directions. And it's going to come along here, and that wave function is going to travel through both slits at the same time, and then that will interfere with itself. So the electron wave, the electron probability, or the electron wave function will interfere with itself so that you end up with this probability density at this location that looks like the interference pattern. And then when you actually make the measurement, the relative probability of detecting something at this location versus at this location, meaning at this location here versus this location here, is set by the amplitude of the wave function. The square of the amplitude of the wave function gives you that. And that's how the electron knows where to land and where not to land. You can do a thing where you can actually detect which hole it comes through. You can put a detector behind one of these holes, and that actually tells you whether the electron came through one direction or came through the other direction. That performs a measurement on the wave function. And so so here's this wave function, it comes through, it goes through both holes at the same time, then you make a measurement. So this is giving you the canonical interpretation of quantum mechanics. You make a measurement to that location, and that collapses the wave function. So it's no longer interfering with itself in the same manner. And what you end up with is, instead of an interference pattern like this, you get two bright spots. So you get those electrons that go through this hole and those electrons that go through this hole. But that's a consequence of having this measurement device that's just outside of here. So that's pretty weird. What's a quantum eraser? I don't actually know what a quantum eraser is. I probably did know, but it's one of those things where you look it up and you read it and you're like, yeah, I got it, and then you forget about it in a little bit. Okay, so here's a question. I always wondered about the idea that it travels through both slits. It's always talked about detecting it at one slit will destroy the wave. What if you detect it in both slits? Well, you can only detect an electron in one location. Like it's going to have some fixed location when you actually make the detection. By putting the detector here that tells you that yes, the electron went through this particular slit. It's not that the electron went through that slit. It's that the wave function went through both slits. And then you made a measurement based upon the probability density. So when you have this thing coming through both slits, the probability density is going to follow these two sources, right? You have these two sources of waves like that, and then they're going to combine to create this interference pattern. So the wave function travels through both slits. You make a measurement immediately behind one of the slits, and that is going to say, let me rephrase that. The probability density here at the screen is going to look like the interference pattern. The probability density here, right behind the slits, is going to look very different, right? This probability density is going to look like this. So when you make the measurement, it's either going to be here or it's going to be here. So you make the measurement there. That kind of forces the wave function to, now the electron is at this location, so that localizes the wave function to that place, at which point it's going to spread out, and then you're going to get your bright spot here or your bright spot here, because now you have this basically 50-50 probability density because of the amplitude of the wave after it's like immediately after the slit. You don't get the interference pattern until you're out here, and that those probability waves or the overall wave function is able to interfere with itself over some distance to produce that. Okay, here's the question. How does the detector change the wave to just two spots? It's not that the detector changes the wave. It's that if you were to map the wave function, so here's your wave function coming along, it's got some distribution. You have these two slits like this. Right here at this position, the wave function actually looks like this. Okay, and it's not until because this is going to act like a point source, this is going to act like a point source. And if we look at, let me pull up interference from two slits water. See if we can see a good, yeah, okay, we'll pull this one up. This looks pretty good. So right behind the slit, so this is the area right behind the slit right here. You can see that there's basically this bump and there's this bump. Let me pull this up. Yeah, or maybe I'll pull this one up. We'll steal whoever's image this was. We'll steal it. Okay, right behind the slit, like at the location of the slit, you'll notice that the wave function is there or it's here. Okay, and it's not until you get farther away from the holes where you develop this large-scale interference pattern. So as you come in closer, the wave function itself actually has that bimodal property. And so when you're making a detection at that location, then you're saying, I've detected, here's the wave function. The wave function of the electron makes it through these two slits. It has some shape because of the presence of those slits. And then I make a measurement which forces the electron to choose some location where it's measured. At that point, the wave function is different, right? The wave function has now been perturbed by my measurement device. And now I have a wave function centered at the location where I measured the electron. And then that wave function expands. And when that wave function expands, it's going to expand, in in some forward direction. It's going to have some, it's going to diffuse outwards. It's going to has some transverse momentum that's going to spread the wave function out. But either way, you're going to end up with a bright spot there or a bright spot up here. The bright spot up here is for when the measurement is not made at that location. That's the equivalent of making a measurement, right? That Rush song where it's like, if you choose not to decide, you still have made a choice. So if it chooses not to go through here, but that's effectively a detection of the electron up here at this part of the wave function. And so then that's going to propagate outwards and create the other spot. Okay. All right, let's see. I thought of an experiment that might be interesting. What if you arrange the slits like a tic-tac-toe pattern, put a detector in one of the horizontal slits, but it collapses, it still can go through either of the vertical slits. What does the electron do? That is a good question. I don't have an answer to that question. What you'd have to do is the same idea where you say, like, what does the wave function look like as it propagates through the 4 slits? What it might mean is that you get an interference pattern in one direction, but not in the other direction. So one could imagine, so I'm shooting from the hip here, but one could imagine that if you had 4 slits that are set up like this, and you put a detector on one of them, because you should get an interference pattern coming across, connecting these 2 holes and connecting these 2 holes. And so by measuring it in one of them, there's 3 different interference patterns that you're going to produce in something like this. And so my suspicion is that you would actually see 4 dots. But I might be misinterpreting what you're saying here. How is the measurement done? So the measurements in this case would be done by having some chamber where you build up the voltage, and if an electron comes through, then it's going to cause a little bit of, it changes the voltage somewhat and causes a little spark to happen or something like that. So you have something where if there's an electron that passes through, the moving electron is going to induce a magnetic field. So it's, when the electron goes by, it's coupled to the electromagnetic field, and then you can have something in there that detects changes to the electromagnetic field. So it's fairly straightforward way to do. I don't know what it looks like because I haven't done it myself, but this is an experiment that was done many, many, many years ago. And so it's a fairly straightforward way. There are straightforward ways of making this kind of measurement. Okay, so my interpretation, if that's a fair word here, is that your measurement changes the wave function because the act of measurement isn't interference on the... So the act of making the measurement perturbs the system, right? You've now entangled your detector in with the system. Now, I'm not a quantum mechanics purist. I don't know what the right term is. I don't think about the deep implications of quantum mechanics. I just say, this is what the Copenhagen interpretation is, and that's the one that I was taught and that most people are taught. There's other interpretations that people like a lot more because it's got reasons that they have in their mind. I don't know that I necessarily buy them. I think there's this wave function and it propagates in some direction. The interpretations don't really make that much difference in terms of the outcomes. But there are people that are still thinking about, what are there tests that one could run that would distinguish between the Copenhagen interpretation and something else? So there are some movies or some YouTube videos by Sabine Hassenfelder. I think that's her name, where she talks about some of the arguments that are going on don't seem to be really moving science anywhere, but it's also outside of my discipline. So there are a bunch of people who have their own opinions about what's the right interpretation of quantum mechanics, like the many worlds hypothesis, that every time there's a quantum decision that ever has to be made ever in the history of ever, that you spawn a whole new universe. I don't know that I buy that. It seems like that's overkill to be able that for every quantum measurement that you've made, there's a whole new universe that's the same size as ours but different. I don't know that seems a bit beyond the needs. Like, we just have a problem of like, what does it mean to describe the wave function collapse, and we're creating a new universe every tiny fraction of a second, right? Billions and billions of new universes every second. Just seems like a bit of overkill. Okay, what am I missing from this? We did Huygens principle. We did the Young's double slit experiment. We did single slit diffraction to some extent. We covered that, right? That's where if you constrict the wave in one direction, it will spread out. So we talked about that. We have not done polarization. We've already covered. And so we need to talk about thin film interference, which is amazing. Thin film interference is a great topic. So here, thin film interference is basically saying, okay, so you have this layer, and it's partially reflective. So you have light that comes in, you have a wave that comes in like this and bounces off the top layer. You have another wave that comes down like this and bounces off the bottom layer. And depending upon the wavelength of the light that comes in, so this has some fixed thickness, or a variable thickness, right? It could be different. But let's pretend for the moment that it has a fixed thickness. Then light that comes in at a given angle, this ray here, or that wavefront, will interfere with this wavefront here, off of this, where they reflect on the surface. And if the path length, the extra path length that one of them travels, so this extra path length here, is equal to an integer number of wavelengths, then they'll come out and they will add constructively. If it's equal to a half integer number of wavelengths, then they add destructively. So light comes in, a fraction of it bounces off the top layer, a fraction bounces off the bottom layer. If the wavelength is such that the extra path length traveled, that you can fit an integer number of wavelengths into that extra path, then they will come out adding coherently, and then that will show up. You'll be able to see it. You can see it. If that path difference happens to correspond to a half integer number of wavelengths, then they're out of phase and you don't see it. And it's a wavelength dependent, right? If you have a longer wavelength, then maybe you fit it in. If you have then it doesn't fit the right number. If you have a shorter wavelength, then maybe it does fit the right number, and so forth. And that actually gives you this figure here. So what you're seeing here is soap in a ring. So here's a ring. You have some soap bubbles. So you're going to blow bubbles and make all the children happy. And you'll notice that the rainbow, you see all the colors of the rainbow. So the reason you see all the colors of the rainbow is because at the specific thickness, so it's illuminated by white light. White light is coming in and bouncing off of it. So white light comes in, bounces off of this, and comes back. And it corresponds to, at this location, or at this latitude, we'll call it, here, or the height above the middle, that is where you get the red light is the right wavelength, so that the red light goes in, and the reflection off of the front surface of the soap film and the reflection off the back surface of the soap film are an integer number of red wavelengths. And that's going to be true at every point along here where there's red. And then the blue is going to show up where it's the right thickness for blue light to reflect, and green is going to show up where it's the right thickness for green, and yellow, and so forth. So all the colors are separated here based upon the thickness of this soap. So what's happening here, this is illuminated directly. So all the light is coming in parallel. It's not coming in at some angle. So you could imagine having light coming in at a different angle, for example, and then you have a different path length, right? This angle, you have this huge path length here, where if you're coming in straight, for example, then you got a small path length, just the thickness, twice the thickness. And so you'll get different colors depending on the angle that you see. So if you have a film that's like this and you're looking at it from an angle, then maybe this angle is coming in like that, and you get one interference pattern where the light, the light's coming from the sun. So here's light coming down from the sun. Maybe the light that's coming in like that at a different angle is going to be a different color. So this will be like blue, and this one will be red. And so when you look at an oil slick on the surface, you're actually looking at light coming from a different angle. That's one of the things that can be going on. Another thing that can be going on is that you actually just have different thicknesses. So in the case of this soap ring, the thickness, so here's the ring, the thickness is actually changing. The soap is going to stretch like that. And so you get different thicknesses at these different heights, and that's going to correspond to constructive or destructive interference for different colors of light. And then when you get down here, where it's quite a bit thicker than the wavelength of light, they tend to wash out because there's going to be ripples in the surface. There's going to be surface imperfections along here, and so it's you're going to get mixtures of light. It doesn't cleanly separate them the way that it does if you're down here talking about small numbers of wavelengths that fit in that gap. Okay, so that's what's going on down here. So you get really good contrast up here, and then as it gets thicker and thicker and thicker, then it tolerates more deviations. It tolerates more wavelengths because of the fact that up here, for example, you're talking about like 2 wavelengths. Down here, you're going to be talking about 10 wavelengths? So this is like 10 wavelengths. So small deviations in the surface at 2 wavelengths is a large fraction of the width of the of this thing, where small deviations in the width down here are going to correspond to well, the same size deviations down here are going to correspond to a smaller fraction of the total width of the thing. And so that's so you're going to go from, like, if you go from 2 to 2.2, that's a 10% difference. If you go from 10 wavelengths to 10.2 wavelengths, so that this is the size of the deviation, going from 2 wavelengths to 2.2 wavelengths is a 10% deviation, which is a fairly significant change in the thickness relative to the wavelength. Down here, it's 10 to 10.2, and this is like, what, a 2%? This is 2% as opposed to 10%. And so deviations in the thickness of the soap band down here are going to not be as important, and therefore the pattern washes out. That's what's going on here. So the pattern is really prominent here, and then it washes out as you get further down. It's still there, but it does wash out. What's going on up at the top here is not that there's no film there. What happens at the top is that the thickness of the film is so thin that it's smaller than one wavelength. So you have light coming in at a given wavelength, and if the wavelength of light is, you know, like this big, then it's not even a full wavelength here. And so you get reflection off of this and reflection off of that, and the nature of the reflections is such that they there's essentially no path length compared to the wavelength up here. This thickness here is much, much smaller, so that thickness is much, much less than a wavelength. And so you don't even have to worry about the path length difference. Instead, you get the fact that when you have a reflection, depending upon the nature of the reflection, you will get, it will cause the wave to flip over. So basically, if you go from a low index of refraction to a high index of refraction, then it causes the wavelength to flip over. And if you go from a high index of refraction to a low index of refraction, which would be, so in the one case you're going from air to soap, in the other case you're going from soap to air. Like soap, so here's your soap. You have air up here, and you have air down here. So if you go from air to soap, which is what you have with this reflection, then it flips the wave over. If you go from soap to air, then the wave doesn't flip over, which means it's directly out of phase immediately. And there's no effective change in the wavelength there. And so it automatically comes out destructive interference. So once it gets thin enough, you basically have the reflection from the near surface and the reflection from the far surface happening at the same wavelength, or within one wavelength of each other. And so they come out destructively interfering, and that's why you get this black up here. So that's pure destructive interference. If this was an oil slick, for example, so where you have air and then soap, or air and then oil and then water, then you might not get that property when it gets really thin on the edges. So that's kind of cool. All right, let's see. Quick question. I was showing my daughter how to charge glow-in-the-dark stickers with white light and then discharge the glow with red light. It works. Interesting. I figured this was a quantum effect of interference. It probably has to do, so I don't know. Typically what happens when you have a glow-in-the-dark stick is that you have some atomic structure. So these are the allowed electron levels in your atomic structure in your material. And then you have some state up here. There's actually, you need 2 states. Okay. And what will happen is you'll take an electron from this state, you'll hit it with white light. White light, it doesn't necessarily need to be white light. It needs to be light that has the wavelength that corresponds to this transition. So that needs to be included. And that, because glow-in-the-dark things are kind of plastic, they're a little bit amorphous, these are relatively broad bands of what wavelength will actually cause this excitation. So, but you could charge something glow-in-the-dark with one specific color, namely the specific color that corresponds to this transition from the valence electrons in your substance up to this excited state. And white light does that because white light spans the whole thing. Okay, so, and then what happens is it will go from here, which is a short-lived state, down to this location here, which is a long-lived state. So this transition happens over the course of, and it's an atomic transition. We're probably talking about like millionths of a second, maybe less. This one, the transition from this location down, so this location up, that's a fast transition. This is also a fast transition. But from this location down, that one's a slow transition. It's forbidden for whatever reason, because it's got angular momentum, the angular momentum state of the electron here doesn't correspond to the angular momentum state down here, and so in order to conserve it, you have to go through you have to emit some photon with some certain properties that, or you get a virtual particle that allows this transition to happen. So you have some forbidden transition here because there's some quantum number that you need to have another particle come in to facilitate the interaction to allow all the quantum numbers to be preserved. So this is a metastable state where it will stay there for a long time and then it will jump down. And this is what you see that's the glow in the dark part. So you charge it up from this state, you put it in a metastable state, and then over time this will fall down with some probability, and so you get a decay of the glow in the dark thing, and this is the green light that comes out. So it's typically going to be like the ultraviolet light that charges it up, some higher energy light that charges it up because you have to get it from the valence state up to this excited state here. This happens on its own, but that's a really small transition. So I'm wondering if what might happen, I don't know for sure, but what might be happening with your glow in the dark thing is that you have your metastable state and you might be shining red light on it, which corresponds to this transition back up to here, which then allows it to jump back down quickly. So you have it up here, it's in the metastable state, and you're bumping it from the metastable state back up to the excited state, which can go through the fast transition, the reverse of the transition that put it up in that excited state to begin with. So that, it would be my guess. And it makes a letter M, so it must be right. That would be my guess as to what's going on there, is that this is probably a red light transition here, this is the green light transition, and then this would be some kind of like in the blue or near ultraviolet or something like that that causes that one. Like whatever the energy sum is between the red and the green. Okay, let's see. Question here. Could that technique be used to make lasers since it isolates and separates light? So that technique with the thin film interference, it's not usually, so you can separate specific wavelengths with thin film interference. So that is something that can happen. There are more efficient ways of doing it. So like a diffraction grating is a more efficient way of doing it than using thin film interference, but it can happen, right? So you shine light on something, you have a film. Well, okay, here's an example. So it doesn't correspond to, making a laser, but coatings on your glasses, like anti-blue coatings and things like that, do use this thin film interference. Like you put on the coating of your glasses specifically so that it either blocks or transmits, so it either reflects or transmits light of specific wavelengths. So like laser eyeglasses, laser safety glasses, I want to keep this one up here because it's a cool picture. So laser safety glasses. Notice that they're different colors. So this is a 532 nanometer safety glasses. That doesn't look right, to be honest. If it's 532 nanometer safety glasses, then, okay, so this depends upon, all right, so let's take a look at some images here. 532 nanometers is in the green, okay? So now that's weird. That's an interesting thing. Isn't that like what Magneto wears? That looks like Magneto. Oh, check that one out. Now that is amazing. That's amazing. All right, so anyways, notice that they're different colors. The reason that the safety glasses are different colors is because they're designed for specific lines. They're designed for specific laser color. Lasers have very narrow spectrum, and so they correspond to specific wavelengths. And so you choose your glasses so that wavelength reflects off of your glasses, and the other wavelengths can go through. Now, one issue with these safety glasses is that you can't tell if the laser's on or not because you can't see it. It reflects off of your glasses. So you have to have some other way of detecting the fact that the laser is turned on. Now, some of these things, like this says 532 nanometers, but it's in the color here is weird. This actually implies that they're being illuminated from behind, even though the shadows don't seem to indicate that. Because if they are green and you're illuminating them from the front, it will reflect the green and it will allow the red light to transmit through. Where if they're illuminated from behind, then it's the red light that transmits through, which is why they appear red, and the green light will reflect off of it. So if you have 532 wavelength things, then it's that wavelength that gets, well, maybe it's absorption. they might design it so that it absorbs that wavelength. Usually, the ones that I've had that are 532 nanometer are actually green in color, like these ones, like this, so that it's actually reflecting the green. But I can imagine that you design them so that they absorb a specific wavelength. You get it to bounce around a bunch of times, and then it absorbs it. So anyways, you can also get goggle wavelengths that correspond to twice that frequency. So a 532 nanometer wavelength is actually a 1064 nanometer laser that has a frequency doubling crystal in it that combines two photons that are in the infrared. So 1064 nanometers is in the near infrared. There's a crystal in there that is a frequency doubling crystal. So it takes two photons at 1064 nanometers, combines them in such a way that you get one 532 nanometer wavelength coming out. And so the green pointers is actually an infrared laser that goes through one of those crystals and then produces green light coming out the other end. So one of the things you have to be concerned about with lasers, especially the green pointers, is the fact that it's actually not a green laser. It is an infrared laser with some power, and then you have this crystal in there that doubles the frequency and gives you the green wavelength. You can have a laser classification is based upon what is the power of the laser light that comes out. So they were, at some point in the past, there was a manufacturing issue where they didn't have a filter in there to block the 1064 nanometers. So you were emitting, here's your laser pointer. You have a 1064 nanometer light coming in. You have your frequency doubling crystal that it's not 100% efficient. So, you have some green light that comes out. You want this to be bright enough for someone to see, which means that you have to have a powerful enough infrared laser over here in order to account for the inefficiency of the conversion process to get a beam that comes out that is the right, has the right brightness. But all this 1064 stuff is also going through. So these are the ones that you want, and then you still have all this 1064 that's coming through that's in the infrared. And so you can see the green, but you can't see the infrared. And so the problem, what you're supposed to do when you make something like this, is that you insert a filter right here. It has to be after the frequency doubling crystal. If it's before the frequency doubling crystal, then nothing comes out. But you put a filter here that absorbs all of the infrared light, and then only the green light comes out. Okay, and then what you do is you measure what's the intensity of the light coming out that's green, or the intensity coming out, and it's only the green light that comes out. And therefore it's like, oh, this is 5 milliwatts, and that corresponds to a class 3 plus or whatever type laser, and this one's safe to operate in classrooms. But they were making some, and it was a Chinese company at the time, were making them that was missing this filter. This filter was gone, and so it might have been 5 milliwatts coming out of here, but it might have been like 50 milliwatts that was being produced in the infrared. And this is a different class of laser because it causes different amounts of damage to your eye. And because that wasn't being filtered out, you actually had what looked like a 5 milliwatt green laser was actually a 50 milliwatt infrared laser with 5 milliwatts in the green. And so at Fermilab, we had to go through, and the safety people, not me particularly, but although it affected me because we were using these types of things in our setup, they had to go through and safety check each one of the laser pointers and insert a filter on their own in order to bring it back down to the right classification. So that was pretty gnarly, fun to do. Okay, let's see. All right, so there we go. That's somehow we got onto lasers, but that's lasers. We talked about interference, talked about diffraction. Did we miss anything? I don't think we missed anything here. Thin film interference, so that's what we're looking at with thin film interference. Oh, so let me show you another example of how thin film interference is applied in the manufacturing thing. When you do thin film interference, you can be really specific about what wavelengths you want reflected and what wavelengths you don't want reflected. So if you were to look at the reflectivity, I spelled that wrong, but that's okay, of aluminum or silver. So we'll go with silver. So you have a silver mirror, reflectivity of silver like this. Silver mirror, which is like what you'd have, you wouldn't have a silver mirror at your home, it'd be like an aluminum mirror. But you can see that silver has a high reflectivity, like way above 90%. Aluminum has a really good one as well, and it's way cheaper. But here's silver right here, and it's high reflectivity, above 90% for most of the visible wavelengths, so visible lights in this area. And so that's why silver looks the way that it does. On the other hand, if you if you look at the mirrors of LIGO, so LIGO mirror, they look transparent. Roughly transparent, right? They're green. So here's a LIGO mirror. It looks green. You can see this kind of red color and then this green. So this is what the LIGO mirrors look like. Because they're specifically designed to reflect 1064 nanometer light. So they use that laser that I showed you, except they don't have the frequency doubling crystal. So it's 1064 nanometer light that's coming in. You want to reflect 1064 nanometers, which means that you are going to, well, so the behavior of the 1064 nanometers is going to be different. The reflective properties at 1064 nanometers is going to be different than the reflective properties at 532 nanometers. So you choose a coating so that it reflects that infrared light. I think what's going on here is that you have the thing thick enough so that it's an integer number of 1064 nanometer light, which also implies that it's an integer number of 532 nanometer light, right? If you have 2 wavelengths of 1064 nanometers, that's 4 wavelengths of 532 nanometers. And so what you're seeing here is the reflectivity or the reflectance of this thin film in the green, which is half the wavelength that it actually operates at. But it's specifically designed to reflect the infrared wavelengths. But it's transparent at all the other wavelengths, and that's why you can see through it, right? You can see here that they can see through it to the other things as long as you're observing those in a different wavelength. So that's kind of cool. That's what's going on with these LIGO mirrors. That's a mirror, but it's a mirror that's specifically designed to reflect one wavelength. Then what you can do is you can do diagnostics with other wavelengths. So you have another color, a different wavelength. There are other greens, there are other red lasers that aren't at these wavelengths. And so you can align the laser, or you can align it with some other laser color if you needed to. You can do some diagnostic tests with different colored lasers that would transmit through there into a detector that's behind it. And so it would basically, it wouldn't bounce off the mirror. You specifically chose the mirror coating to reflect specific wavelengths. So, and that's thin film interference. So these kind of coatings, you see the same kind of coatings on like camera lenses and things like that. That's what's going on. Okay, any questions on this? So here's the plan. The plan is that next time we will talk about special relativity. So we'll do special relativity next time, and then we're going to look at all these great chapters that are coming up. So we've got, 5 more chapters, 6 more chapters. We've got special relativity, so that'll be fairly straightforward. And then we're going to do quantum mechanics, atomic physics. We'll talk about interesting stuff that's going on here, interesting stuff with radioactivity and nuclear physics. That, of course, is going to be everyone's favorite section. Particle physics and the Yukawa forces and the basic forces, all this kind of stuff is going on here. But that gets us through the end of optics.